How's everyone doing? Good, I'm assuming. All right. Well, let's get started. And then if my computer dies, well, then my computer dies. All right. Let us begin. So, hopefully everybody's doing good. Some announcements today. Class today is obviously online. Tomorrow, class will also be online. And my office hours tomorrow will be virtual as well. I probably won't be in that full time, so email me if you're going to come to office hours. Send me an email really quick to let me know. Otherwise, I'll probably cut it a little short. Okay. Don't forget about homework 3 is due Monday night at 11:59 p.m. It's over definition of the derivative stuff. You should be able to do all of it technically now. What you learned today is going to make the last third of it a lot easier. Okay, so but homework 3 due Monday night at 11:59 p.m. You definitely are able to do all of it right now. Okay. So are there any questions about homework or meeting tomorrow or office hours or anything like that? Saba asked me that after class so I can clarify what you mean. All right. So today we're going to talk about the power rule. If anyone's taken Calc 1 before, they probably have seen the power rule, and you probably use it all the time, even though I asked for the definition of the derivative to evaluate a derivative. Okay, and so this is everybody's favorite rule. It is a very useful rule, and you are going to be using it all the time because it lets us, along with a few other simple rules, it lets us calculate derivatives of any polynomial and a lot of algebraic functions that are written in a way that might not look like you should be able to use the power rule. We're going to see how to do those types of problems today. So here we go. So the power rule for differentiation, if n is a real number, so n can be any real number here, okay, then the derivative with respect to x of x to the n, well, the way you do this derivative of this power is you say this is n times x. So you take the exponent and you bring it out in front of the x, and you multiply it, and then you subtract 1 from the exponent to get the new exponent. N times x to the n minus 1. Okay. This works for any real number n. I'm only going to prove it today for positive integers. Later, you'll have the tools to be able to prove it in general. Right now, we only have the tools to prove it for positive integers. Okay, so before I prove this, I'm going to ask a question. I think I probably know the answer already. How many people know the binomial theorem? Show of yes or no in the chat, or the little symbols, you know. Yeah, I don't think most people don't know it, and that's fine. It's something that your high school teachers are technically supposed to teach you, and then no one ever does. So know that this is something that your high school teachers failed you on as far as teaching you. But the binomial theorem is a theorem for expanding stuff like x plus h to the n, okay, where n is an integer, a positive integer. And in short, x plus h to the n is going to be, well, the first term is going to be x to the n. Then the next term, and this is just by the binomial theorem, okay, the next term is going to be n times x to the n minus 1 times h. And then the next term is n times n minus 1 divided by 2 times x to the n minus 2 times h squared. And then every other term, if you keep adding terms, the terms with x's, the powers are decreasing every term. And the terms with h's, the power on the h is increasing with every term. So the next term is going to have an h cubed plus something with an h to the fourth, and so on, all the way to the very last term, which has an h to the n. Okay. So I'm skipping over what these coefficients should be. If you want to know, you can just ask me. They actually don't affect the proof at all. The only thing that really affects the proof is this one. So if you trust me on that one, and trust me, that's right, then the rest of the proof follows pretty easily. So if we want to show that the limit as h approaches 0 of, well, I'll call f of x to the n here. So the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. We want to show that this limit exists, right? If it does, that's the derivative with respect to x of x to the n. Okay, well, this is the limit as h approaches 0, the limit as h approaches 0. F of x plus h, well, that's just this guy right here. Okay, so x plus h to the n minus f of x, well, that's just x to the n, all divided by h, right? All right, so then I'm going to plug in this big thing for x plus h to the n. So this is equal to the limit as h approaches 0 of x to the n plus n times x to the n minus 1 h plus, and then everything else is going to have at least an h squared in it, right? This term has an h squared, this term has an h to the third, this term has an h to the fourth, and so on. So I'm just going to write plus h squared times something. Okay. So that's me just writing everything up here in a very lazy way. So there's x plus h to the n, and I'm going to subtract off x to the n and divide by h. Okay, so what happens here? Who can tell me what happens here? There's one pretty obvious thing, I think. So you might want to answer the obvious thing first.
Do some of the
x
h's
to the n.
Yeah. So I got both answers. So I'll do the easier one first. So x to the n's cancel, and then someone said a lot of the h's are going to cancel, and that's exactly right. Once the x to the n cancels with the minus x to the n, then every single term up top has at least one h. So I'm going to cancel that h with that h, and we have one h left there. Okay, so after all this cancellation, we're left with the limit 0 of n times x to the n minus 1. Again, that comes from canceling off the h here. And then plus h times, again, I could write this stuff out, but hopefully you see that when we don't have an h in the bottom, so that there's really no need to write out the stuff in the parentheses, because when we can plug in h equals 0 now, it is just going to go away. So now that I've canceled h from the denominator, there's no harm in just plugging in h equals 0, and I'm left with n times x to the n minus 1. Okay. And that is what we were trying to find, the derivative with respect to x of x to the n. Are there any questions about this? I know the binomial theorem part requires some trust that I'm not just making that up. But other than that, did everything make sense to you guys? Okay, so I had an extra page. There we go. So let's use the power rule to find the derivatives of the following functions. All right, so we've got f of x is pi to the 5th. Let's do this one first. I want to find f prime of x using the power rule. So what am I going to get? I'm tricking you guys, just so you know. This one's a trick. I am tricking you. So what am I going to get here? Yeah. In the chat, someone said, you're tricking me, it's 0. Yes, pi to the 5th is a constant, right? Pi to the 5th, there's no x's in here. So when I take the derivative with respect to x, well, another way to think of this is you could write this as pi to the 5th times x to the 0, right? X to the 0 is just 1. And so if you think about using the power rule here, well, you would bring this 0 out in front, and so whatever you get, you're multiplying by 0, and you're going to get f prime is 0. Okay, this is like this is always the first question any calculus teacher asks right after you learn the power rule to make sure you're paying attention. So the derivative of a constant is 0. And we actually already showed that, but with the power rule, it's nice that the power rule kind of jives with that. Okay. All right. How can I use the power rule for number 2 here? I want to find g prime of x if g of x is equal to the 4th root of x. This doesn't seem like a power rule problem at all. So what could I do? Someone who hasn't answered. What does the 4th root of x mean? Yeah, exactly. X to the 1/4. Someone in the chat said x to the 1/4, right? So g of x is the 4th root of x, but another way we write that is x to the 1/4. And the reason why is x to the 1/4, I mean, the whole thing behind this is if I raise it to the 4, then I should get back x. But the way we simplify exponents, this is going to give me x to the 1/4 times 4, x to the 1. So it's exactly what we expect. And that's why we write it as x to the 1/4. Okay. So now looking at it like this, what is g prime of x? Well, my exponent is 1/4. So what do I do with that? I boop it out in front. So I'm going to get 1/4 times x to the 1/4 minus 1. And so that's 1/4 times x to the what? X to the 1/4 minus 1. Well, what's 1 minus 1/4? Gotta say something.
1/4
Negative
x to the
3/4.
negative 3/4.
Yes, thank you. Negative 3/4 here. Very good. And so if you want, you could rewrite this as 1 over the negative exponent. I can bring that down into the denominator. You could write this as 1 over 4x to the 3/4 if you want. You could leave it like that as well. So either of these answers is perfectly acceptable. Okay. All right. And then number 3, we want to take the derivative of h of x is equal to 1 over x to the 7th. So h prime of x. Well, how am I going to rewrite this to be able to use the power rule?
X to the negative 7.
Perfect. This is x to the negative 7. And so using the power rule, what happens? H prime of x is equal to, well, the exponent, always you boop that out to the front. So negative 7 times x to the what?
-8th.
Perfect, -8. Again, if you want, you can leave it like this. You could also bring the negative exponent back down into the denominator. Negative 7x to the 8. Okay. Either answer is fine with me. Are there any questions about using the power rule? Simplifying expressions so that you can use the power rule? Okay. Get myself some extra room there. All right, so I mentioned that this rule is going to let us take the derivative of any polynomial, but we haven't really proved how to handle A, constant multiples of a function when I take the derivative, and B, when I'm adding two functions. And polynomials are just powers of x with some coefficients, and you add them together, right? So I need to handle first how do I handle sums of functions, and how do I handle constant multiples of functions. So if f is differentiable, so that means f prime of x exists, and a is a real number, then the derivative of a times f of x, well, the constant just pulls out from the derivative. And so we just get a times f prime of x here. But you don't have to take my word for it. We can prove it. Okay, so let's prove it ourselves. So a times f of x prime. We want to find this. This is the limit as h approaches 0 of a times f of x plus h, right? Because whatever your function is, you plug in x plus h. And then minus a times f of x divided by h. And so what do this term and this term have in common?
a f of x.
Yeah, exactly. They both have a not quite an f of x because x plus h inside this guy messes that up a little bit, but they both have an a out in front, right? So I can factor the a out. So this is a times f of x plus h minus f of x all divided by h. And now for limits, we did have the rule that if I have some constant times some function when I'm looking at the limit, the constant can just come out in front of the limit because the constant doesn't depend on h at all. So this is a times the limit as h approaches 0, f of x plus h minus f of x divided by h. And what is this bit here?
F prime x.
Yeah, perfect. That is just the definition of f prime of x. So then this whole thing is equal to a times f prime of x, exactly what we wanted to show. Okay, so that's one that might feel intuitive, but it's definitely good to be able to prove intuitive things in math because sometimes the intuitive things are the hardest things to prove. Okay, so are there any questions on constant multiples of functions and taking their derivatives? All right, so sort of related to that, let's say we have two functions that we know are differentiable, which again, that just means f prime exists and g prime exists. Then we can look at their sum or difference and try and take the derivative there. And so who has a guess as to what the derivative of f plus g is going to be?
F prime of x plus or minus g prime of x.
Perfect. It's just going to be the sum or difference of the derivatives. So this is usually stated, the derivative of a sum is the sum of the derivatives. Okay. So this results, again, you don't have to take my word for it. We can prove it for ourselves. So I'm going to call f plus g of x. I'm going to call it f g h I j k. I don't know. Let's call it s of x, just so I don't have to keep writing out. All right, so I want to find s prime of x, right? But by definition, that's the limit as h approaches 0 of s of x plus h minus s of x divided by h. All right, what is s of x plus h equal to? This just means everywhere I see an x over here, plug in x plus h over here and here. So what do I get when I plug in x plus h into s?
Sx plus sh.
Ooh, careful, because we don't know how f and g. I want an answer in terms of f and g, not just in terms of s.
Fx plus gx plus h.
That's close. So we don't know how f handles f of x plus h. So I can't simplify f of x plus h any more than just plugging that in like that. The only thing I can do and guarantee that it's right is just write it like this: f of x plus h plus g of x plus h. So again, this s of x plus h, all that means is everywhere you see an x, you plug in x plus h over here. So this is equal to the limit as h approaches 0. Well, s of x plus h, that's f of x plus h, plus g of x plus h, minus s of x, that's minus f of x, plus g of x minus the whole thing, and then all divided by h. Okay. So then if we rewrite this a little bit, reorder some things, this is the limit as h approaches 0 of, well, if I distribute my negative here and here, I'm going to get f of x plus h minus an f of x when I reorder some things, plus g of x plus h minus g of x all over h. Okay. Are there any questions on that so far? Okay, well, we can then, I can break this up into this plus that, right? If I'm adding two things over the same common denominator, then I can break them up into two parts still over the same denominator. So this is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, and then, well, plus g of x plus h minus g of x all divided by h, right? And then what can I do with the limit of a sum? If I'm taking the limit of the sum of a sum of two things, what did we say we could do with that?
Give it to both times.
Yeah, exactly. You can break this up into the sum of the limit of two things. So this is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h, and then plus the limit as h approaches 0 of g of x plus h minus g of x divided by h. All right, and then so what is this?
F prime of x.
Perfect. And then what is this?
G prime of x.
Perfect. G prime of x. So what we showed was s of x, remember s of x was f plus g, or f of x plus g of x. And we just showed that s prime of x then is f prime of x plus g prime of x. Okay. So derivatives of sums are pretty simple to compute. You just take the sum of the derivatives. Don't let this convince you that when you take the derivative of a product, that it's just going to be the product of derivatives. We're going to see that that's going to be very wrong. We have to use what's called the product rule, which we'll learn about either tomorrow or next week. Okay, so let's look at some examples. Compute the derivatives of the following functions. 1, f of x is x to the 5th plus 16x squared minus 3 over x cubed. 2, g of x is equal to the square root of x minus 2 over the square root of x. And 3, h of x is pi over x to the 3rd minus pi to the 10th. Okay, so let's look at this one first. I have f of x is equal to x to the 5th, or sorry, x to the 5 halves, plus 16 x to the 2 minus 3x cubed. Okay, and I need to take f prime of x. So what do? I can, by the last problem, well, I really only dealt with the sum of two things, right? So, but, I mean, then you can think of this minus this as another separate thing. So really what we proved is not very hard to show that you can, if you take the derivative of sum of any number of things, then you can just apply the derivative to each separate term. Okay, so f prime of x, I need to take the derivative of this plus the derivative of this minus the derivative of this, right? So then what is the derivative of the first part? What's the derivative of x to the 5 halves?
5 halves x to the 3 halves x.
5 halves x to the 3 halves. Perfect. And there's no x on the top. Just you bring this out in front, and then you subtract 1 from 5 halves. For anyone having trouble doing that in your head, that's okay. 1 is just 2 over 2, right? So that gives you, that's where the 3 halves comes from. That's why it's 3 halves and not 4 halves. Okay, excellent. All right, so that's the derivative of the first part. Plus, now I can just take the derivative of this part. So what's the derivative of 16 times x squared?
32x.
Perfect. 32 times x. Because again, the 16 is just is a constant multiplied by x squared. So when I take the derivative, the 16 just comes along for the ride. And then I use the power rule on x squared. The 2 comes out in front. I get 16 times 2 is 32 times x to the 1. Perfect. Minus. All right, so what's the last term going to be? Well, how could I rewrite this?
3x to the power negative 3.
Perfect. Or oops, I gotta have my negative 3. There we go. Yeah, and so what am I going to get when I take the derivative of this thing?
Negative 9x to the negative 4th.
Perfect. Negative 9x to the negative 3 minus 1, so negative 4. All right, and notice that we keep this minus out in front here. Oops, I don't want that to look like an equals. We keep that minus right there. And then we are also getting a minus from when we bring the negative 3 down in the front. So overall, this is going to become minus 9. That's going to be a plus 9 there at the end. So we're going to get 5 halves, x to the 3 halves, plus 32x, plus 9 times x to the minus 4. Okay. Are there any questions on that? Cool. So the next problem we wanted to look at was g of x is square root of x minus 2 over the square root of x. All right, so I want to find g prime of x. Well, it's going to help to rewrite this so that I have powers of x, right? So how can I rewrite that in terms of powers of x instead of square roots? In calculus, you'll find we don't like the square root symbol. We like to always rewrite that as a power.
X squared, maybe?
Not quite. That's a good guess, but there's
To the power 1 by 2.
yeah, x to the power 1/2. We want when we square it, it's going to get rid of the square root, and so in order for that to be the case, we need x to the power 1/2. So that when I square that, I'll get the exponent will be 1/2 times 2, right? So that's why the square root of x is x to the 1/2. And then minus 2 over x to the 1/2, but how can I rewrite that? How can I rewrite 2 over x to the 1/2 so that I have just x to a power? Someone in the chat says, perfect, x to the minus 1/2. Exactly. Because I can't really, everybody sees that we don't have a rule to deal with something yet that's just in the denominator. But if I have x to a power that's in the denominator, then I can rewrite that like this, right? Okay, so what is g prime of x then? Well, I'm just taking a sum of a couple of things, so I can just apply the derivative to each part separately. So what's the derivative of x to the 1/2?
1/2 x to the negative 1/2.
1/2 x to the negative 1/2. Perfect. And what's the derivative of 2 times x to the minus 1/2?
Negative 1x to the negative 3/2.
Careful, that was very, very close. But this minus, we're going to have a 2 times, or so minus, the 2 comes along for the ride, and then that will be times negative 1/2. And then that's times x to the minus 3/2. So I agree that we have this minus here, but overall it's going to become a plus, okay? Because negative 2 times negative 1/2 is going to give me plus 1. Okay. Are there any questions on that? Cool. And then the last one was h of x is pi over x to the third minus pi to the 10th. H of x is pi over x to the third minus pi to the 10. I want to find h prime of x. Well, it's going to, again, you're always going to want to rewrite this in terms of x to some powers, right? So how can I rewrite this as just x to some power times a constant? Yeah, exactly. Oh, go for it. I much prefer you guys to speak on your microphones, by the way, if you're able. You were going to say, I heard a pi.
X to the negative 3.
Perfect. Pi times x to the negative 3. And then I don't have to do anything with this one, minus pi to the 10. So h prime of x, again, I've got a sum, or really a difference here of stuff, so I can just do the derivative separately. Derivative here, derivative here. So what's the derivative of pi times x to the minus 3? Well, pi is a constant, so it's just going to come along for the ride. So I can just write down pi. And what's the derivative of x to the minus 3?
Negative 3x to the negative 4.
Perfect. Negative 3x to the negative 4. Perfect. And then what's the derivative of minus pi to the 10th?
0.
Ah, I didn't trick anybody. It's 0. That's right. Pi to the 10th is a constant. So its derivative with respect to x is 0. Okay. And so overall, this derivative is negative 3 pi times x to the minus 4. Okay. You're all too smart for me. Did I go too fast? Does anybody have any questions on any of these problems here? All right. So with the last 10 minutes, let's look at this problem here. Find the equation of the tangent line to the graph of the function f of x is x to the 2/3 at x equals 8. So your final answer should be what? Just tell me what. Should it be a number? Should it be an equation? What should your final answer
Should it be the equation of a line?
Perfect. My final answer should be the equation of a line, which we in this class either write as y minus y1 equals m times x minus x1, or if you want, you could go y equals mx plus b. I'm almost always going to prefer this form. Okay, so in order to get my final answer, I need a slope and a point on the line, right? And so, yeah, someone in the chat said if we need a slope, then that again should set off alarms in your head, and you should think what?
Derivative.
Derivative, exactly right. So the only function I could possibly take a derivative of is f of x here. So I want f prime specifically at what point? Oh, did I plot this? No, I didn't. Okay. I want f prime at what?
X equals 8.
At x equals 8. Perfect. So f prime of 8. Okay. So before, when we only knew the definition of the derivative, we might have looked at the limit as h approaches 0 of f of 8 plus h minus f of 8 divided by h. This is specifically f prime of 8. Now, with the power rule, it's actually much easier to just find f prime of x immediately and then plug in 8. Okay. It's also more convenient if you're doing a problem where you need to plug in multiple different values for whatever reason. Okay, so we're not going to be doing this, delete. We're going to first find f prime of x. So what is f prime of x here? Well, I just have x to a power. So f prime of x is
2/3 x to the negative 1/3.
2/3 x to the negative 1/3. Perfect. By the way, with these problems, it might help to have a sketch of a graph of what we even want. So x to the 2/3 looks roughly like this. It actually has a cusp at x equals 0. It's supposed to be symmetric about the y-axis, but I'm doing a very horrible job showing that. And then, so over here, we want 1, 2, 3, 4, 5, 6, 7, 8. We want to find the slope of that line. That's what we're trying to find right now, right? But again, that's just going to be f prime of 8. So f prime of 8 then, well, that's going to give me 2/3 times 8 to the minus 1/3, which it might be easier to rewrite this as 2/3 times 1/8 to the 1/3, right? So what's 8 to the 1/3?
3 or 2, sorry.
Yeah, there we go. Perfect. So this is 2/3 times 8 to the 1/3 is just 2, so 1/2. So we're going to get boom, boom, f prime of 8 is equal to 1/3. So now I have m, and now I just need a point on the line. But looking at my graph, what point, or what's the x coordinate going to be of the point on the line?
8.
8, perfect. So I just need the point 8 f of 8, right? That point is going to be on the line. So what is f of 8? Well, f of 8 is just 8 to the 2/3. And this is simply 8 to the 1/3 squared, right? So what's 8 to the 1/3 again?
2.
That was 2, and so this is going to give me 2 squared, which is 4, right? So we just showed that the point 8, 4 is on the line, and we know that the slope, which again, that's just derivative at x equals 8, is 1/3. Okay, so then I can use my point slope form of a line to say that my final answer is what? Who can tell me what to write here? The line, so I'm definitely going to have a y.
-4
Perfect. -4.
equals
Perfect.
1/3
1/3.
x minus 8.
X minus 8. Perfect. And you can just leave your answer in this form if you want. I always just leave my answer in this form. Because again, this gives you all the information you need to know to plot the line. You know that the point 8, 4 is on the line, and you know the slope. So from the point 8,4, you can go up 1/3 to get another point on the line and draw the line. Okay. Are there any questions on this? Finding tangent lines is going to be a big part of this class. Okay. So in the last, here we go, last 4 minutes. For what x's does the function f of x equal x squared minus 10x plus 14 have a horizontal tangent line? So what does it mean to have a horizontal tangent line?
The slope of it, the derivative of 0 is 0.
Perfect. Yeah, if I have just a horizontal line in general, then I know that it looks like this. The slope here, well, the rise is 0, and then the run can be whatever you want. But m here is 0, right? So slope, again, that should set off alarms that say derivative. So slope f prime of x is equal to 0. This is the equation we want to solve. So what is f prime of x for us? Who can tell me? Well, I can just take the derivative piece by piece, right? When I'm adding stuff. So what's the derivative of x squared?
2x
2x. What's the derivative of minus 10x?
minus 10,
Minus 10. What's the derivative of plus 14?
0.
0. So I get f prime of x is 2x minus 10. And then I want to set this equal to, because I'm finding where the tangent line has a horizontal slope. I want to set that equal to 0, right? So what x value gives me a horizontal slope? Or a horizontal tangent line, rather, sorry.
5.
Perfect. You just add 10, 2x is equal to 10, and so x is equal to 5. That's the only point that gives us a horizontal tangent line. Yes, perfect. Thank you, Saba. Are there any questions on this? Because this type of calculation is also going to come up quite a lot. Okay. Well, that's all I have for you. You should definitely be able to do all of the homework without a doubt. So tomorrow we're going to talk a little bit about the product rule, which you won't need on this homework, but definitely on the next homework. And then we'll go from there. Okay. So if there's no questions, feel free to sign off, and I'll see you guys tomorrow.
Thank you.
Thank you.
Thanks.
Thank you.